So I want to today present to you the latest and greatest that we've been up to at NIST in Gaithersburg with Ian Spielman and his group. And we've been working on disorder gauge fields for atomic Bose gases. So first, a little flavor for you, a little motivation. So here are the two quintessential AMO disorder experiments probing Anderson type localization in matter waves. On the left, you have an experiment featuring a 1D disordered lattice. And on the right, the potential is speckle disorder. So in both cases, what you do is you suddenly shut off the main trapping potential and allow the system to expand in these disordered potentials. And what you'll see is past a certain point where you crank up the relative disorder strength, the system remains localized, as you can see here, proving Anderson's prediction made more than 50 years ago. And now we understand this is an interference effect. Another thing that we're interested in is the ability to inject angular momentum into our Bose-Einstein condensates. So this will involve some sort of stirring of laser beams or literally rotating the entire quantum gas or something more complicated. But the main point is here, around a vortex, your phase must wind as an integer multiple of 2 pi. And so if you look at images of what these clouds look like in this situation, you'll see these characteristic dips in the density and a clear footprint of vortex formation. And what we're looking for is to actually sort of synthesize both of these things together and do some interesting new things. So from a bird's eye view on the topic of disorder, you might get the impression that disorder is actually quite elusive because depending on the size of your system, its dimensionality, the symmetries that govern it, you might get different emergent effects. So for example, for 3 dimensions, we typically expect a metal to insulator transition and mobility edges. And for lower dimensions, the sort of common wisdom is all disordered states are at the very least weakly localized. On the right here, we have a phase diagram for a type 2 superconductor. So in between the Meissner phase where the magnetic field gets completely shut out of the material and you have superconductivity, and on the opposite end, you have the normal phase where the magnetic field is fully penetrating and there's no superconductivity. There is an in-between vortex phase where some magnetic field does penetrate the material. We have vortex nucleation in the same way as in the images I showed you before in BCs, but now in an actual physical material. And we have the ability to support superconductivity. So to do what we want to do, the tools are already there. So we use control fields to coerce the atoms to do the things we want them to do. And we use all kinds of control fields. So for example, cooling of atoms, all kinds of potentials, scalar potentials, and so on. So you know all this. So for example, here is a novel way you can engineer a 1D Dirac Hamiltonian with linear dispersion relations using RF and magnetic field dressing. But I'm not going to talk about that today. Today I'm going to talk about the ability to engineer synthetic gauge fields using Raman transitions. So this is going to be the main workhorse going forward, so I'm going to try to explain to you what's going on here. So I want you to think about 2-photon Raman transitions, and in that case, obviously you should think about in units of the wavelength of the lasers and also the recoil energy imparted on an atom as it absorbs a photon from any of these arms here on the coupling scheme. So if you were to draw the single particle energy dispersions corresponding to this coupling scheme, you'll see something like this. And if you turn your attention to the blue here, which is the ground band, you'll see that as you move away from the resonance of these Raman transitions, you'll see that the ground band here, we can move the energy minimum and its corresponding momentum value of the entire system with the detuning. So, and I'm going to call this value the K-min, which is quite literally, if you were to describe the effective Hamiltonian of the system, you'll see that this is the vector potential type term affecting describing the effective dynamics here in the system. So quite literally, we have a knob, the detuning, that allows us to change the vector potential here. So that's what we're going to use. So here's a quick little experiment you can do to verify that this is a gauge field in case you don't believe me. So if you run a detuning gradient, you'll notice that you can create the sort of current sheet geometry in the vector potential with a constant magnetic field. So if you adiabatically load the system into the state, then snap everything off, allow everything to expand in time of flight, you'll see these beautiful time of flight images with quantized vortices. So indeed, this is a gauge field. But we can't use this tool to do disordered gauge fields because this was done using magnetic field generating coils that don't have the resolution that we need experimentally. We want something with fine control. So the goal is we want to be able to engineer arbitrary detuning patterns. So to that effect, we're going to add to our existing Raman beams another coupling arm here, and we're going to run an electric field from below orthogonal to the axes of the Raman momentum. And we're going to use a digital mirror device to shape the intensity profile of this thing. So in case you don't know what a digital mirror device is, just imagine a 2D grid of pinholes where we have the ability to address each and every pinhole and control whether light passes through it or not. So then the name of the game is we can create arbitrary detuning patterns here. They're going to pass through the imaging system, and the atoms will be able to interpret an arbitrary light shift. So that's how we're going to control the detuning here. Alrighty. So first, let's start with something simple before we get into complicated things. So let's go to the high energy regime. We're going to use the Hamiltonian as a unitary evolution operator, so we're going to pulse the Raman on suddenly. And if you start in the rubidium E7 ground state, particularly in MF0 in this case, in the F1 manifold, you'll see Rabi flopping that looks like this. So this is a highly out of equilibrium kind of physics we're looking at here for now. And if you're nominally unresonant with the Raman, you'll get experimental data that looks like this. Now, if you apply a small detuning, you'll see that the detuning comes out as an imbalance in the magnetically sensitive state. So there's an imbalance in the +1 or the -1. And if you take some experimental images, for example, for a nominally uniform detuning pattern, shot to shot, there's nothing interesting going on as you would expect, just maybe a little bit of experimental noise and a little fuzziness. Ow. All right, now let's do something fun. So now if you do a bunch of experimental shots changing random detuning patterns that the atoms are going to see, you're going to see some wild stuff going on here. So there's actually quite some surprising things going on even here, but I just want you to focus on the +1 and -1 spin orders here, where you'll see that in the random detuning case, sometimes there's more atoms in +1, -1. So you can see that the magnetization sort of fluctuates wildly shot to shot. So if you plot the variance of the magnetization versus the disorder strength of the detuning patterns that we're sending to the atoms, you'll see that the experimental data in gray versus Monte Carlo simulations of single particle trajectories where we feed the detunings that we think the atoms should be seeing based on our simulations of the imaging system, you'll see that things are in quite nice agreement. So this is just a NIST way of confirming that the atoms are seeing what we think they're seeing. Now let's do something a little more complicated. So now let's try to reproduce the vortex nucleation data that I showed you at sort of the beginning of my talk. But now let's do this using light. So I'm going to load into the Raman dress state now, and we're going to probe a lower energy regime. So now not only is the detuning important that we're sending, but if you calculate a gradient along the detuning, along the axis that's orthogonal to the Raman momentum, you'll see that there is a synthetic magnetic field that the atoms are interpreting. And now you can think of flux, you can think of angular momentum entering the system, and once again, vortices. So we're going to increase the gradient strength now, and we're going to see what's going to happen. We should hopefully reproduce the same results. So as we keep increasing the gradient strength, eventually it becomes more energetically favorable for vortices to enter the system. But how this happens is abrupt. So you see, as you keep increasing the gradient strength, then boom, this happens. I'm just going to increase it a little bit more. So you see that two vortices are in the smack dab middle of the cloud here, slicing it into three pieces. And the specifics of this have to do with the fact that our BC is very elongated, and also it's a finite size system. So if you're curious to learn more, there's this paper by Lund that sort of explains how to understand all these things. All right. So if you were to plot the shearing parameter, which is this angular quantity that does this sort of weird thing to our BC in time of flight, you'll see that there is indeed an abrupt step-like jump that is a signature of vortex nucleation. And if you were to compare this to old data taken with the magnetic field generating coils, you see that qualitatively you have the exact same effect. So really, this is just a demonstration that we can create the same exact things using optical fields and optical fields only. All right. So now I have 3 minutes to show you the real meat of the experiment. This is the fun part. So what happens with the disordered gauge field? So we're going to load into the Raman dress state once again. And there are actually some complicated things going on here that I don't have time to explain, but I just want to give you an intuition of what to expect from disordered vector potentials. So we're loading into the Raman dress state, and we're applying these patterns here. So we're going to start with a uniform one, and we're going to keep increasing the disorder strength once again. So as you keep increasing it, interesting things start happening. So first, let me point out to you, if you traverse the in situ extent of our BC, which is this red dashed line, you'll see that depending on where you are, the magnetic field will point up or down. So in some places, you're inducing clockwise rotations. Other places, the rotations are counterclockwise. So you can sort of try to draw an analogy to the shearing data I showed you before, but now vortex formation is happening sort of wildly. And from the images, you can tell that there is a signature of vortex formation. You can see some very similar patterns that we saw with the uniform gradient case. And if we keep increasing the disorder strength, so you can probably barely see what's going on here, you see that we've populated a huge swath of momenta values in terms of the state of the system. So let me just enhance things a little bit here for you to see. So you'll see that we've covered a huge range of momenta values now, doing something crazy to the Raman state. And you can draw some single particle intuition for what's going on here. So if you were to consult the single particle dispersions, you'll see that if we feed a large detuning value to the system, there's this scalar bowing effect. So from these time of flight images, you can actually deduce more or less what the detuning, what kind of detunings you're sampling in the system. And because of this, you can actually, because we're in Raman, the distances between the spins must be two recoil momenta. So you know that this blob here and this blob here are correlated, for example, and the same applies here for this blob and this blob. But this is a single particle intuition. What single particle physics cannot explain is, are we nucleating vortices? And we're still working on the many body simulations to really do the sort of surgical confirmation that this is truly happening. But that's sort of the main result of our work so far. So I have 30 seconds left. So that's sort of all I wanted to show you today. Let me just give you a flavor of some more interesting things we will be doing going forward. So the important thing is you can start with a sort of backwards problem where you start with a target magnetic field that you want to have and work your way backwards, doing some calculus, if you will, to figure out what kind of what you want to command on the hardware to really get the magnetic field that you like. So for example, here is a type magnetic sort of structure, and in the real world, we really can't do it perfectly because of some limitations in how we're limited we're bounded in the intensity here. So things have to go back and forth and come back. But there are certain structures you can make, for example, to do vortex spinning experiments. If you want to learn more, there's this paper by Victor Galitsky and his colleague on arXiv that sort of explain what's going on with these zero flux on average kind of patterns here. And that's it. So I just want to thank my colleagues Alina and Emmanuel, who are basically the only reason that this experiment works at all. So anyway, so thank you very much, and please, if you have any questions.
Thanks a lot. Other questions? Yes.
Yes, please.
Nice talk, thank you.
Thank you.
Quite at the beginning, you have this ground state curve, which is displacing K. So the ground state is drifting?
Oh my God, I have to go all the way
that's
back.
why I asked that question.
Sorry about this. You meant this, right? Uh-huh. Yes, that's right. So indeed, the point is that this appears when you just very carefully and adiabatically load the system into this configuration. So if you just take many milliseconds and slowly and gently load the system into that state, you will really see this in the time of flight images because we do track the momentum, and you will see it. You will see it. You will see it come out. Yep.
Okay. There's another question.
Yeah, no, really good talk. Very interesting. I just had a question, but just out of interest.
Yes.
So this is a very nice way of introducing magnetic fields into this situation.
Yes.
Can you still implement things like photonic lattices to still have like a periodic potential, like added into your BEC to still model those kind of things? Or?
Oh, of course. So I think what you're asking is, can we add other potentials on top of this whole thing? And yes, because, well, actually we were planning on this experiment is 3D. We were planning to have a sheet trap where we do 2D experiments in disorder, but we realized that in 3D we can also see transitions between localization and delocalization, so we didn't do it. But you can do basically all those things that you described exactly. Yeah, we were just things happened and we didn't.
Okay. Thanks a lot.
All right, thank you very much.
Thanks a lot again for your talk, and let's thank the speaker again.